Mhm.
Okay, so let me start. Let me comment that I'm going to go relatively quickly over each of the topics. If this is meant as over tease more than anything else, to get people a sense of the problem, not to teach you the great details of quantum circuits and how to design these circuits, but to give you a general understanding and to give you a perspective on the overall problems. And of course, I can answer questions. If you want a lot of papers I cite, you can go to my website, which is mentioned here. So please, by all means, contact me if you have any questions. Okay. So I'm going to quickly go over, the basic application space, which is basically cloud computing. The important keyword here is stationary. Just because I think it's important to give credit where it's due, I want to give a brief history of supernativity as a field, and then I'll get into the topic of SFQ and what it looks like. SFQ is the acronym for single flux quantum. Then the heart of the talk will be this topic of large-scale superconductive Biosite complexity systems, and then I'll summarize. Okay, so this just says cloud computing is important. We all know it. It's the computing world has evolved from mainframes to personal computers to mobile computers. Now all the action is in cloud computing. It's shocking how much research is being placed in this area. And this just says clearly that energy of the cloud computing portion of the system is high and only increasing. So there's some shockingly large number, like 4 to 5% of the total energy of the planet is being spent on cloud computing, data centers, things of that sort. And clearly we want to improve that. So, we're looking at different solutions. Well, CMOS is a technology that we all know well, and I've been doing it for a long time, but we need another technology that can be lower energy. And so one such technology is superconductive electronics. There's a variety of different families of superconductive electronics. The most mature and most well-known form of this logic family is something called single flux quantum, or SFQ circuits. We encode data as quanta, which I'll describe in a few minutes. And fundamentally, it's cryogenic. So, you can't make this into a cell phone. But for things like cloud computing, where it's stationary, it makes a lot of sense. And you have to operate at very low temperatures on the order of 4K, very cold. But we can get to exascale computing. We can do it in a very power efficient way, and we can save a lot of energy. So it's exciting. And this is really the application space, and it's much smaller and much denser. So let's just talk about Summativity just quickly. One of the things that you need to understand is superconductive signals are not, lines are not just low resistance. They're exactly zero DC resistance. There is an AC resistance, but there's a DC resistance, which is zero, which is quite interesting. And the current, given as long as it's maintained cryogenically, can persist forever, literally forever. You also have this Meissner effect, which is where magnetic fields are expelled from superconductors. And the trick is you want to maintain the temperature below some critical temperature, which we call TC, and that varies for the materials. And so for the most common material is niobium, another one is niobium nitrate. But niobium, you cool it down to 10K. So often what we do is just cool it at helium. So there are magical temperatures for different materials. One famous one we all know is nitrogen, which is at 77K. Niobium is at helium is at 4.2K. So we cool it down to 4.2K, and we can then maintain superconductive material inside this niobium line. This concept was actually discovered a long time ago, but more than 100 years ago, by a fellow named Onnes in the Netherlands. And he basically was able to liquefy helium and show this superconductive behavior. And it was kind of an important result. This is an early example of it. And then a series of very important researchers followed. The London brothers did some very important work in characterizing the behavior, and now they're called the London equations. Famously, Vitalik Ginzburg and Lev Landau, I actually met Ginzburg once, did some very important work in the area of Summativity. And this is all formulated together in what's called the Bardeen, Cooper, or Schrieffer BCS theory. And so this is where we describe the effects of Cooper pairs, which and where the supercurrent is composed of these Cooper pairs. So the current isn't a charge, it's pairs of Cooper pairs, which is quite interesting. And by the way, just as a little side comment, Bardeen also won a Nobel with Shockley for the transistor. So he was quite an important, prolific, and capable person. Okay, so along comes Brian Josephson, And he basically invented the Josephson junction, which is a very important result. It demonstrated tunneling through a superconductive Cooper pairs, no DC current drop. And this was the key junction or device that we now use in all our devices. Followed up, and even within my own department, there was a very important result from a fellow named Sidney Shapiro, who discovered what's called the Shapiro steps, and they're defining characteristic of Supernativity, and other people did important work at Bell Labs. So this gives you a sense of some of the famous people involved. And along came in the middle 80s something called high temperature superconductivity. So the acronym that we use is HTS versus low temperature, or LTS. And so in 86, Bezos and Mueller discovered in IBM this concept of superconductivity operation at much higher temperatures, not room temperature, but much higher. Initially, it was in 30K, and they've moved it up much higher to minus 40 degrees centigrade, and very high critical fields. But there's some interesting applications, and there's a lot of work, and it's they're still developing a theory for it. Here's an example of some of the materials that people have developed over the last couple of years. Knows the temperature is increasing to higher and higher, and we define LTS and HTS here, and 77K being the boiling temperature of liquid nitrogen being the reference or calibration point for the two temperature zones. So there's a lot of classical applications in superconductivity. Electromagnets, you've heard of superconductive trains and things of that sort. Squid magnetometers. Voltage references are very common. The ultimate voltage reference is a superconductive device. People, there are companies that make a lot of money producing voltage references. And then there's an application which we call energy efficient electronic circuits, which of course is my interest. And there's lots of different applications. It's been around for a while, particularly in space. And the reason being, the ambient of space is relatively low temperature, on the order of 2.7K. So you've got it built into the system. So you don't have to cool, you just put it up there. And so that's been around. And when I was in industry a long time ago, we were working on this very area of space electronics based on superconductive circuits. There's a lot of military applications where they want very high precision, radar, AD conversion, things of that sort. And that was something that's been around a long time. But the one that's most exciting is cloud computing. And you get the idea. Low energy data centers, you can now improve the energy by orders of magnitude and maintain in higher speed operation, as long as we mature the technology. And there's a new application, which is a very hot one, as we all know. Not hot is a joke. Cold quantum computing, which is operating not a millikelvin temperatures. And so SFQ is a natural interface with these millivolt signals required by the qubits. And so you see a lot of work now in control and readout of quantum computers. And so these are the applications. And it's kind of diverged into, I mean, space and military will have been around and are not going anywhere, but cloud computing and quantum computing are the two primary new application spaces that people are working on. And so here's an example of the temperature interfaces for a quantum computer. And what you see is SFQ operating as the control logic into the quantum array of qubits. And so this is a very important topic. It's very interesting, and it's a growth path in terms of research. Lots of funding, lots of interest, and I'm being pulled into it myself. Okay, so let's really get into what we want to talk about, which is single flux quantum circuits. Okay, so you have these two superconductive layers separated by a weak link. You've got an insulator and a normal metal layer, and there are classic voltage phase relationships and current phase relationships. These are the standard, it's not V equals IR, it's a different set of expressions. But what you see is that the phase difference across the junction is an important parameter. The critical current, which is when it goes normal. So people talk into superconductor behavior and normal operation. So when you exceed the critical current or temperature or magnetic field, it looks like a resistor. It looks like a normal piece of material. And so the trick is to switch it between superconductive and normal behavior, and it produces this interesting quantum flux, which is expressed by this expression, h over 2e. So this is the classic expression for the quantum flux, and basically the design of these circuits is the process of pushing around these quantum flux from gate to gate to gate, and we do it in a way shown here. So we represent a logic state 1 as the existence of a quantum flux pulse. If if you don't have any quantum flux pulse, then you have its logic state 0. That's the core idea. What's interesting about these pulses, they have a quantized area of precisely 2.07 millivolts per picoseconds. So that's a very, and so you see millivolt kinds of signals. And so one of the issues is interfacing to CMOS is not such an easy thing because you're dealing with 500 to 1,000 millivolts, but also interfacing to qubits is a natural thing because now you're dealing with millivolt levels, and that's quite good. So we produce these over SFU pulses using overdamped JJs, which means it's a resistive characteristic in there. We have a DC bias current that sets it with respect to the critical current. And I want to point out, just to be fair, that there's a variety of other logic families. There's extremely low power technology called AQFP. There's a very relatively mature technology that's based on AC biasing called RQL. There's other DC bias circuitry like ESFQ and dual rail. So there's a family of different technologies that have been invented. I want to point out that the core paper, that the famous paper for this was by Konstantin Likarev and Semenov from Russia, and they invented this RSFQ logic family that has now been becoming has become the dominant SFQ superconductor digital logic family. Okay, so why do we care? And this is, of course, the reason. Here's CMOS, which is a good technology, and you can do many hundreds of billions of devices. So it's a great technology. But superconductive electronics, we're talking about 2 to 3 orders, 100 to 1,000 times lower energy per operation. So if you're dealing with watts, you're dealing with milliwatts, and that's a big difference. And if you're dealing with thousands of watts, which is what a data center would be, or even much more than that, orders of magnitude, 2 or 3 orders of magnitude less, and that makes all the difference in the world. And that includes the cost of the refrigeration when I say lower energy. And there's another element, which is that you can operate these circuits at 10 to hundreds of gigahertz. So we've demonstrated close to a terahertz frequency. I've seen circuits on the order of 880 gigahertz. Tens of gigahertz are straightforward. We're talking picosecond delays. So I mean, you can imagine now, you get gate delays on the order of a couple of picoseconds. You can operate these circuits at very high speeds, 2 to 3 orders of magnitude lower energy. Very exciting. There's one catch, and maturation. We haven't fully matured the technology. And that's where the action is. So there's been a lot of money put into this technology, particularly by the US government, developing and promoting this technology, primarily for data centers. We want to lower the energy. I'll go from there. Yeah, the NSF just recently announced a new Expeditions project, of which I'm part of, to do just this topic of developing SFQ technology. It's going to be based out of USC, and Rochester is a major component. So the technology that we've been dealing with, that we've been using primarily, there's 2 that we use, but the one that I mentioned here is the MIT Lincoln Laboratory. It's funded by the government, and it's got a very efficient technology, and the goal is a million junctions. So it's not billions like CMOS, but millions of junctions. I also mentioned High Press. High Press is a company north of New York City in Elmsford, which they also have a fabrication facility for superconductor devices, and they do a variety, and that's commercial, and you can talk to them, and I'm sure they'll sell your product. So the point is that there are a variety of different fab facilities in the US, around the world, in Japan, and it's growing. And so now that focus is in maturing these technologies to get from millions to billions. We want to demonstrate this we want to scale the circuits, we want to use highly regular structures, and there's been a big effort to automate the design. So now, if you can imagine, you've got millions of junctions, you have to be able to automate the process. You can't do that manually. And so there's been a big program by the US government, which I've been part of, to automate the design. It's got a nice name. It's called Super Tools. If you Google it, I'm sure it'll come right up. So Super Tools is a nice program to develop tools for superconductive electronics. It's been around for 4 years. We're in the last year of that project, and it's been producing a lot of major results, which are helping to automate the design process. Okay, so let's get into the heart of our conversation today. One point I want to make is, I've been doing CMOS forever, and since the late 70s, to be honest. And where we are in SFQ reminds me of where we were in CMOS in the middle, late 80s, where we had these devices, we had these interesting results, low power relatively back in the day, but the tools weren't there, the design methodologies weren't there, the flows weren't there, and there were a lot of companies that were jumping into the game. ECAD becoming Cadence, Synopsys, and Mentor, and 20 Daisy, and all those companies developing tools at the time. And it reminds me of that period. So now there's a lot of effort to develop EDA tools for SFQ, to automate the design, the synthesis, simulation, modeling, verification, testability. These are all issues of great currency and importance. And of course, it crosses a variety of different abstraction levels from device all the way to RTL. So it's a big focus and a big action. There's a lot of effort and a lot of recent research in this area. And so what I'm going to talk about today is compartmentalizing these subcategories, and there are a bunch of others. We can go on forever, but I only have half an hour today. So I'm going to talk about power bias distribution. I'm going to talk about synchronization. I'm going to talk about memory issues. Memory is a big issue in SFQ and in superconductive circuits because it doesn't come easy. And there's some recent results that have improved it greatly. I'm going to talk about the basic interconnect characteristics, talk about testability, security, these kinds of ideas. So these are the same points. So across the abstraction levels, we're going to talk about these various topics one by one. We'll start off with the basic issue of how do you connect the various junctions. So there's two classic ways of doing it. Using a JTL, an active Josephson device with an inductive loop to store a state. And basically, if you've got cells that are close to each other or near abutted, you can place one of these JTLs in between and connects A to B. And they take energy, and they take space, and they take the active layers. But it helps, and it regenerates an amplifier. So it regenerates the signal, and it's good for short distance interconnect. If you've got long distance interconnect, all these active JTLs wouldn't make sense. And so people use what's called a passive transmission line. By passive, it's not completely passive. We have a driver and a receiver at the endpoints of the line. But the idea being, if you're going across the chip, you have a big, long superconductive strip line or microstrip line, and you ballistically propagate an SFQ signal from the driver to the receiver, and then it gets converted into the local gate. So it's the classic way to communicate, and lots of publications in these areas. But PTL is how we're going with automated layout techniques because you want to have long lines. Another issue, which I'll get to in a minute or two, is there's a major problem issue with SFQ gates. Unlike CMOS, where you can have multiple fan out, you've got a single pulse. You want to move from A to B. So how do you move from A to more than B? The multiple outputs. How do you produce a fan out of more than one? And there's ways, and we call those ways splitter gates, and which we'll talk about in a few slides. So, but that's a problem. You have to basically take a pulse and convert it into two pulses or more. Another big issue, and I'll get to in a few ways throughout the talk today, is that we in the CMOS world, we're used to talking about capacitance and a little bit of inductance. As a few circuits, we talk about inductance. It's all about inductive magnetic fields, coupling from place to place. And there's a lot of work to do magnetic modeling and understand the sources of noise due to these. And it's not just mutual inductances, it's much more complicated than that. And so there's a lot of effort to have very clear inductive capabilities that be able to extract and model and design with inductances. And part of the issue, as I show down here, is you have inductive loops on purpose. This is how you store a state, which I should have mentioned earlier. You have a Joseph induction here, another one here, and an inductive loop. And you basically store a state, in this case, the one state, and it can stay here forever. Or there's no pulse. But the point is that as long as it's maintained cryogenically, you maintain that state forever. And you worry about coupling between these various points. And so there's been a lot of work in this area. So along those lines, there's another concept which I want to bring up. It's called flux trapping. You can literally think of antenna effects in CMOS. It's the same idea, where you basically have a piece of metal that can trap a magnetic field, and basically disturb that state. And so then pull the magnetic field from the loop, and you lose a state, or you can add a state. And so flux trapping is a phenomenon peculiar to superconductive circuits, and again, very similar to antenna effects. And so there's ways of fixing it. And so the classic way is to have these motes that you distribute around the layout to basically trap the flux and put them in a safe place and keep it away from where the action is. So that's one approach. And in my own group, we've developed other approaches where we have these parallel lines with little resistors, milliohm resistors, to pull the magnetic flux into a safe place. And lots of, I have a variety of different works coming out in this area. One's shown here, but I have more. describing the issues of flux trapping and how to mitigate the phenomenon. And so the general area of routing is important. There's a whole area of guidelines that need to be developed. And there's trade-offs, different kinds of interconnect, JTL for short, PTL for long and medium level interconnects. And depending upon the line widths and the characteristics, what you'll note here is that every time you add a JTL, you've added a delay. The PTL is pretty much a constant delay. You pay for the driver and the receiver, and the interconnect is DC resistance is zero. There's no delay. So the point is that it works pretty effectively. And that brings up an issue shown here with PTLs, where you actually have reflectances in this, this low impedance line or zero impedance line. It bounces from the source to the receiver and back to the source. So you actually have to be concerned about the length of the line and what the time of flight is. And that affects, and we have this in CMOS too, but it's a much more dramatic issue in SFQ. And so therefore you want to partition with the system into repeaters, which is the same idea in CMOS, where you integrate and insert repeaters to separate, to ensure you never have that critical resonance length to worry about. And we have equations here that characterize it, and this has been published and well described. It's a known phenomenon. So this is the idea of splitters. And so the thing about splitters is every time you got a fan out greater than 1, you need a splitter, with a few exceptions. And so there's been work in my group and other groups to actually look at other kinds of other ways of doing splitters to produce more than a fan out of 2, 3, or 4, and basically save area. Because this is a weakness of SFQ. The number of gates you need to include to support multiple fan outs can approach the number of gates you do for logic. And that's not good. And so we're looking at ways to decrease the amount of gates you need to provide multiple fan out. And that's what just evidenced here in recent publications only a few months. So that's just a basic background in the area of interconnect. Let's talk about synchronization. And I need to speed up a little bit. And so different kinds of logic gates, different kinds of clocking methodologies. Gauss is a very common approach, asynchronous and fully synchronous. We've looked at clock tree scheduling applied to SFQ, clock tree synthesis, and so you've got CTS coupled with clock tree scheduling. So there's been work in this area. It's what a TCAP paper is coming out shown here. There's a variety of different ways of doing clock tree scheduling to provide the right delay. And we've tested it on the AMD 29 layout, and we've shown, again, note the gates and splitters being approximately the same amount, which is a problem, but we can automate the synthesis of, and the thing about SFQ, almost every gate needs a clock. And so there's a lot of load on that line. But again, we have ways of doing it. So, and the skews are relatively small, as you see. We also have ways of storing states dynamically. And so this is the idea here, is that you want to have a dynamic logic to, rather than having to synchronize every logic gate, we actually use something called DSFQ, which was recently developed at IBM by a fellow named Rylev. And he's shown approaches where you can actually replace a CMOS gate with an SFQ clock gate with a dynamic gate, which behaves similar to a CMOS gate and doesn't need to be individually synchronized. And so there's been a lot of recent work on using DSFQ as a logic family. And we've done some work here as well in the area of designing multiple inputs, multiple structures, and multiple logic gates based on DSFQ. To continue, important area is bias distribution. So we have to, every one of these gates has to be defined. Every junction has to be set by a critical current. And remember, what you do is you apply a pulse which flips the junction and generates this SFQ pulse when it goes into normal operation. So there's a lot of effort on power distribution or current distribution to improve the robustness. And this has been a relatively underdeveloped area, and it's very important. So we've been looking at ways of doing bias distribution. You have to worry about resistively. There's a lot. So people use a resistive tree, a kind of a voltage divider. That's the classic way of doing it, but that's expensive power-wise. So people have now moved to an inductive distribution system shown here, and there's other issues. And notice the junctions are now in here as well, and you have to make sure that the clock frequency is the highest. This voltage is the highest voltage and the highest frequency on the system, so that it doesn't generate additional pulses. And there's something called a feeding JTL that's been developed to basically drive these circuitry, and we've developed guidelines and methodologies to allow us to know how to best to feed and distribute these pulses, the current, to be able to bias every junction such that when they flip properly in the proper condition. So this is an important issue. And you see when people have built circuits, this is one that came out of high press, where they built a circuit, and that includes these kinds of structures to basically evaluate and develop guidelines for automated synthesis. We've developed a variety of different guidelines ourselves for underbiased conditions, for overbiased conditions, and it's published in the TVSI paper here just recently. So these are issues that come into play. Another issue is simply the amount of current that you have to deal with. And so this is a problem. And so SFQ, superconductive circuits tend to be IO limited. And so we tend to want to have multiple currents come in, but you can't afford the IO. So the idea of current recycling is an important concept, where you actually recycle current from one logic block or chip to another logic block or chip, reusing the current and using transformers to basically form the interface between the blocks. So this has been an area of research. We show some work here where we did some partitioning of the blocks to ensure that that we can move from gate to gate and block to block and save current. Memory is a big issue in SFQ. We can use cryogenic DRAM, and that's been looked at, but the power issues is important, the ambient environment. People looked at MTJs for some of the memory, and people have looked at special kind of devices to literally heat up the device and drive has an interface between SFQ and MTJs. Importantly, there's been a very nice development out of Northwestern, where they invented a 3-terminal superconductive SFQ device that's superconductor, ferromagnetic, and insulator layers. And this gives us the ability to have a pass transistor. So now we have a path to having superconductive memory. There's been a lot of modeling in this area. So I'm optimistic that we can start having superconductive memory. Testability is important. We want to verify functionality. We want to, it's very similar to what's done in CMOS. We want to have access, controllability, observability. These are the key issues in the area of DFT for SFQ. And so we've built a variety of different test point insertion techniques. We've used deflip blocking gates. And so we've created a methodology. This is a relatively older paper, a few years ago, 5 years ago, but we've developed ways to control and manage the distribution of the test point and allow us to improve our testability, both control and observing. We're looking at different structures, bypass devices, and again, very similar to, we basically use the standard CMOS ideas and transpose them into RSFQ. I've got a student now actually working on expanding this into a much more SFQ specific family of DFT techniques, which are important. Lastly, we'll talk about security. Just quickly, these are data centers, and you need to be able to secure the data. And the technology is different, and it's highly sensitive. Often the government, U.S. government's involved. They care about their data, industry cares. So we want to thwart reverse engineering. There's been a lot of different approaches. We use camouflaging. There's been work on developing camouflage techniques, using dummy JJs, operate them as, they look like a superconductor device, but they're just basically a resistor. And so we fake it out in that way. We use logic locking. We have a variety of different techniques that we've used for logic locking and we use the bias currents now as the key rather than some sort of binary structure in CMOS. So we've got different approaches. We've published this paper recently. So security is an important issue. So let me summarize. I only have a few minutes left. I actually have more than expected. So data centers, cloud computing, they continue to increase in demand. This is a big application. The energy of these centers are huge, and we need to fix the problem. CMOS is not going to do it. Maybe cryogenic CMOS can help, but if you're going to go cryogenic, why not go all the way? And the answer is we have to mature SFQ, which isn't ready yet. But that's a lot of money, tens and hundreds of millions of dollars being poured into SFQ right now to fix this problem. Again, SFQ is highly energy efficient, orders of magnitude lower energy, higher speed. You can 200 to 1,000 times lower energy. That's a lot. Operate tens to hundreds of gigahertz. And as long as it's stationary, it's a natural technology for cloud computing. So that's the obvious application. Necessary in quantum computing, totally appropriate in space, and very important applications in the military and certain industrial applications. There's been a lot of work in developing SFQ specific design methodologies, automation. And the goal is to produce real high complexity superconductive systems. We can do it, but not in a generic, general way. And so in the last 4 or 5 years, we put a lot of effort into it. And now we're getting to the point, Synopsys has been a big key element of this effort to develop EDA and algorithm tools. And Synopsys has been driving this for the government, and I'm part of that team, but Synopsys is the key. Other important applications are space and quantum computing, as I've said more than once. I'll mention, just quickly that I wrote a book with one of my students who's now a postdoc in Munich on single flux quantum IC design. It's the only book in the field. The earliest, next book was like 1998, which is more general, and back to 1990. So it's a very recent book, and there's a lot of book topics that go beyond SFQ and just talk about Supernativity, but it's mostly SFQ. So that's the main idea. Thank you, and I have a minute too early. So I'm ready for questions if there are any. I'll stop sharing.
Yeah, thank you very much, Dr. Friedman. Any question for Dr. Friedman? I think we have like maybe a couple of minutes. You can also put your question in the chat and I can read it for him.
Did I go too quick?
No, I think it's okay. That was great. That was a great talk. Thanks.
Sure. Okay.
Any questions? You can maybe raise your hand or.
Okay. So anyways,
yeah,
so
thank you very much.
Yeah, so if people have any specific questions later on, they're welcome to contact me. And good luck with the conference, and good luck everybody.
Yeah, thank you. Thanks.
Take care. Bye-bye.
You too. Bye. Yeah, the next sessions will start in 10-15 minutes. And the sessions are 3A, I'm sorry, PW1, PW2, 3DIC, and 3SS. It will start at 9:45 PST Pacific time.